Our last section in chapter 1, section 1.4, is talking about subsequences and monotone sequences. We'll start off by defining what a subsequence is, but one way of thinking about it is if you have a set, a subset is simply a set that contains some or all of the elements of the original set. Every element in the subset has to be contained in the original set. Well, it's very similar when we talk about a subsequence, the only difference being that order has to be maintained. So here's the definition. It may look a little complicated, but it's not too bad. If we've got a sequence AN given to us, now we have this second sequence, which is a sequence of natural numbers n sub k, as k goes from 1 to infinity, so that's an n1, n2, n3, n4, and so on. It's a sequence with all of them being natural numbers, and this order is preserved. It's an increasing, it's a strictly increasing sequence. Then this right here is a subsequence of the original sequence. A sub nk. Remember, the nks are just natural numbers. They're just indexes. So just to kind of get a picture of what we're talking about, the sequence nk, described right here, is just written out as n1, n2, n3, and so on. And then a nk is a sub n1, a sub n2, a sub n3, and so on. It can be thought of, this sequence A sub nk, the subsequence can be thought of as taking the original sequence A and just removing some terms from it. Deleting terms from the, if you delete terms from the original sequence, you have a subsequence. All right, I'm going to erase just a little bit here, as I can do a couple of simple examples. Actually, maybe I can go right over here. Let's say we have a sequence, AN, a repeating sequence. Just 1, 2, 3, 1, 2, 3, 1, 2, 3 forever. That's our original sequence. I'm going to define n sub k defined as n sub k is equal to 3k. All right, so what does that mean? What then n sub k is equal to what? If I want to list out the elements of nk, what's the first one? Well, the first one is when k is a 1. So it would be 3 times 1 or 3. The second one is going to be when k is a 2. So it'll be 3 times 2 or 6. So that's what the sequence nk looks like. And I'll just make a note that we have n1, n2, n3, n4, and so on. So now let's look at our subsequence, A sub nk. And remember, it's k going from 1 to infinity. We're not indexing on n here, we're indexing on the k. It's going to be n1, n2, n3, which we get from here. So what's that subsequence going to look like? Well, an1, an2, an3, dot, dot, dot. So that's going to be n1 is a 3. Yeah, A6, A9, A12, and so on. So what are those actual elements? Based upon our definition here, it's taking the third element is a 3, 4, 5, 6. The sixth element is a 3. The ninth element will be a 3, and so on. So we're simply getting the sequence, subsequence, 3, 3, 3, ... the constant sequence. So that was a roundabout way of just saying, I want every third element of the original sequence. Before I erase this, suppose I said that, suppose nk is equal to 2k for all natural numbers. What would the subsequence be, ANK? Every other element. In particular, starting with the second one, the even elements. And it's a really easy one to figure out. It's a 2, 1, 3, 2, 1, 3, repeating. And if we picked every third element, starting with the first, it would be the sequence of 1s. We started every third element with the sequence of 2s. But starting with the second element, it would have been nothing but a constant sequence of 2s. One final comment before I erase. Notice, I ran out of room, so I'm going to write a little something down here with regard to this example. What can we say about AN? Well, about the convergence of AN. It doesn't converge. 1, 2, 3, 1, 2, 3. It does not converge to a real number. AN, not convergent. But we defined, well, using this version of ANK, this sequence converges to, that subsequence converges to 3 because it's the constant sequence 3. This one up here, if we used this for the NK, it would have been a non-convergent or a divergent sequence. Remember, that one was the one that was 2, 1, 3, 2, 1, 3, and so on. So what we have here is an example of a sequence that doesn't converge, but we're finding convergent subsequences in it. All right, let's take another example, the one we use frequently. The sequence where each term, AN is just 1 over n. For all natural numbers n. So AN is equal to 1, 1/2, 1/3, 1/4, and so on. We will define 3 subsequences as follows. I'm going to give you the sequence of indexes, the NK sequences. For the first one, we're going to say that NK is equal to 2K, like I had written on the board in the upper right just a minute ago. For all K in the natural numbers. Number 2, in J is going to equal J squared for all J in the natural numbers. Number 3, in lowercase l is going to be 2 raised to the L for all L in the natural numbers. Well, we're going to look at these 3 subsequences. We're going to discuss their convergence or divergence, depending on what they do. And before we do that, though, let's make sure we understand what what the first few terms of these sequences look like. In K, as K goes from 1 to infinity, is going to be what? 2, 4, 6, 8, dot, dot, dot. In 1 would be 2 times 1. In 2 would be 2 times 2, and so on. The second sequence, we would say in J, as J goes from 1 to infinity. What's that going to look like? What are the terms of that, first few terms of that sequence going to look like?
1, 4, 9.
Yep, exactly right. The perfect squares, yeah. The squares of the natural numbers. 1, 4, 9, 16, 25, and 36, and so on. The next one, in sub L, as L goes from 1 to infinity, what's L1? L1 would be 2 to the 1, which is 2. L2 is going to be 2 to the 2nd, which is 4. And then what? What are the next couple of terms? Yeah, the powers of 2, exactly right. 2, 4, 8, 16, and so on. So what I'd like us to do is discuss, and then mathematics, that doesn't mean carry on a whole long conversation. When I say discuss the convergence or divergence of the newly found subsequences, A in K, A in J, and A in L. This one is from K going 1 to infinity. The second one is from J going 1 to infinity. And the third one is from L going 1 to infinity. So by discuss the convergence, divergence, basically I want to say, does it converge, yes or no? If it does, what's it converge to? So I'll just keep the same numbering pattern here. So number 1, we'll do A in K. And let's start off by just writing out the first few terms. Remember what that is. It's A in 1, A in 2, A in 3. But in 1, in 2, and in 3 are 2, 4, 6. So what do we think that subsequence is going to look like? Remember, our original sequence is just the reciprocal sequence, right? The reciprocal of the natural number. So if I want, for example, the 100th term, it's 1 over 100. So I want to start off with this one, since we're using NK as the subscripts of the sequence. I want to just get these terms, the 2nd, the 4th, the 6th, the 8th, and so on. So 1/2, 1/4, 1/6, 1/8, dot, 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 and so on. Any questions on A in K? A in J is A sub in 1, A sub in 2, A sub in 3, where we're using the J's, so in 1 is a 1, in 2 is a 4, in 3 is a 9, in 4 is a 16. So we just need to take because of the definition of the sequence, we just need to say 1 over 1, 1 over 4, 1 over 9, 1 over 16. So the first one is 1 over 1, which is 1, 1 over 4, 1 over 9, 1 over 16, and so on. In this subsequence, the indexes are taken from number 3. N sub L is equal to 2 to the L. And we determined that was 2, 4, 8, 16, the powers of 2. So the first one, what do we start at? Is it 1 or, let's see, it's 2 to the 1, right? So we're starting at 2, is that what we,
Yeah.
correct? 2, if L is a 1, we get 2 to the 1. So we're going to have 1 over 2. Is that what you said, Maddie? I'm not sure.
Okay. That is what I was saying. But
Okay. Yeah, whatever number it is, we just need to take 1 over it. So 1 over 2, 1 over 4, 1 over 8, 1 over 16. So it should be obvious that each one of these 3 subsequences at the bottom was obtained by just removing certain elements from the original set. And this part of it, discuss the convergence or divergence of the subsequences. Well, first, obviously, this converges to 0. And notice that all the subsequences converge to 0 as well. And we'll find out that's always the case. If a sequence converges to a number A, no matter what subsequence you choose, it's also going to converge to A. And that'll be our next theorem. And before I erase this, since I made 3 sequences, subsequences with an NK and an NJ and an NL, each one of them I say, well, AN1, AN2, AN3. I said that for all of them and you can't distinguish between the J's and K's and L's at that point. It might be good to say this sequence converges to 0 as K goes to infinity. The second one, this subsequence converges to 0 as J goes to infinity, because there is no K involved in this one. And in the third one, then we'll use L. This one converges to 0 as L approaches infinity, just to kind of distinguish the indexing schemes we used. All right, well, the next theorem is going to talk about what I just said. A little bit stronger than what I just said. I think I had said that if a sequence is convergent, then every subsequence converges and converges to that same limit. So theorem 1.4. A sequence converges if and only if, remember that's a 2-directional proof when we get to the proof, if and only if each of its subsequences converges. And I'm going to add in a kind of in brackets. In this case, in other words, if we have a convergent subsequence, or we have the situation where all subsequences converge, all of the converging goes to the same limit. Okay, well, this is a 2-part proof. So I've got to do the left implies the right and the right implies the left. And I think the easier of the two is right implies the left. So I'm going to choose to start with that. And I'll make a note like this. So I'm going to assume each subsequence converges in order to prove that the original sequence converges. What do you think I could do? I'll start it off by saying if each subsequence converges, then the sequence converges. I'm just stating it's true. It's obviously true. Anybody think of why it's obviously true? I'll go ahead and put it in brackets here, the justification for it. Why is that? If the subsequence is the sequence itself, which a sequence is a subsequence of itself, right? It just means that your in K would just be all the natural numbers, 1, 2, 3, 4, dot, dot, dot. So a sequence is a subsequence of itself. That's good enough. So if all the subsequences converge, the sequence has to converge because it is a subsequence. Now we will move on to the other direction. It's not difficult, but I am going to use a little mathematical fact that we haven't proven, and it seems very obvious. Maybe I should make you prove it by induction. It would be very, very simple, but I'm going to assume we know this. I'm just going to write it down here, and I'm going to erase it. It's not part of the proof. This is just an observation. If you've got your sequence of increasing natural numbers, like we had a minute ago, give me I'll make the question harder than it needs to be. It sounds harder. Give me a lower bound for this number. Say again? N2. Excellent point. Or actually N2 plus 1, right? Because it has to be bigger. Another way of saying it is just the number 3. Because your natural numbers go like this. So if I had A1, A2, A3, A4, if the smallest this could be is 3, if I'm taking a subset of these, if I leave one out, if I started at 2, if this were the number 2, 3, then 4 would be as small as this one could possibly be. Agree with that? So all I'm saying is that, let me use NK there as an arbitrary term out there. What's a lower bound for NK? True. Yes, that is. Anybody else?
Okay.
Just K.
Okay.
K, because the smallest that number could be is if this has to be a 1 in order to get the smallest. That means it has to go 1, 2, 3, 4, and this one, the smallest it could be is a K. So my whole point of that is that I'm going to use this in the theorem. NK is always bigger than K. Because remember, you're removing some items. You might be removing some items from the list, from the sequence, and you're merging them back to the left. I don't think that description helped at all. But just note that it's impossible. Yeah, try to make this a 2. Well, if that's a 2, this number has to be less than that number, which means it has to be a 1 or smaller, but we're in the natural numbers, so it makes it a 1, which leaves no number for this, no natural number for that. And that was actually what I just said was basically a proof by contradiction, that this is true. But you could easily prove it by induction. And it probably would have taken half that time for me just to prove it by induction. But we'll assume that that statement is true. Okay, now we're going to assume that a sequence converges, implies that each of its subsequents converge, and also to the same limit. So, if we're assuming that a sequence converges, this time I need to name the sequence. We're going to call it AN. So, suppose AN converges to the real number capital A, and to prove the right-hand side, you can't prove every sequence converges individually, every subsequence. You just pick an arbitrary one using variable names, and if it works for that one, it'll work for every subsequence. So let's just say, let A sub n k, k equals 1 to infinity, be a subsequence of the original sequence. And just to let us know what we're doing, I'm going to say it remains only to show, or all we have to do, is what? I've chosen an arbitrary subsequence. We need to show that it converges to A. It remains only to show that A n k converges to A, and we're done. And that'll only take 3 or 4 lines. Well, remember, whenever we want to prove that a sequence is converging, we need to have an epsilon bigger than 0, and then we need to find a capital N. So I will, to save a little room, I'm going to put that epsilon greater than 0 be over there. Let that be given, an arbitrary positive number. Let capital N in the natural numbers be such that, and I'm sure I've told you, but ST means such that n greater than capital N implies, well, we know AN converges to A, so I already know that for whatever epsilon is, there exists a capital N such that little n greater than n means that AN minus A is less than that value of epsilon. So the justification for that one sentence, that this n exists, is because AN converges to A. All right, I think we can get this in one more sentence. Since nk is greater than k for all natural numbers, that's what we talked about on the board just a few minutes ago. Nk is always at least as big as k. Since that is true, n greater than n got this wrong in my notes. It needs to be k. Let's see. N greater than n. N greater than n. Yeah. N greater than n implies nk is greater than n. Because nk is at least as big as n. Which implies in k, let's see, if that's greater than n, that means that A in k minus A is less than epsilon. And I'll make a note. This proves that every subsequence converges to A. Because we arbitrarily chose a subsequence, and we proved that it converges to A. Since we arbitrarily chose it, it could have been any one of them. Okay, so really, because we said that AN converges to A, there's a capital N such that little n bigger than capital N means this is true. Well, all we showed is that our NKs are even bigger than capital N, or at least as big as capital N. And that's what made the proof fairly simple. So if when I'm beating this to death, if we've got a sequence that is converging to this limit, say that's A, it's pretty easy to see that if you just take any infinite, a subsequence has to be infinite, right? You're defining it for all natural numbers. So if you just pick that one, and you picked that one, and you picked that one and that one, you're never going to deviate, you're never going to get far from A. Well, what I mean is that subsequence is kind of obviously from the picture, it's going to converge. Everything you pick is going to be very close to A eventually. Well, one thing that we do at the beginning of discrete math is we talk about propositions, true-false statements. 4 minutes. Thank you. And thank you.